this video, I'll introduce the organometallics, and I'll talk about organolithium, the Grignard, and the organocuprate, and eventually I'll talk about the organoacetylides as well. Um, just as the name specifier, organo means I'm going to be dealing with some sort of carbon, metallics means a metal. So what I'm really looking here is in a carbon a metal bond. So when I'm having a carbon metal bond, we know carbon is going to be more electronegative than the metal. So as a result, I can rewrite this carbon metal bond as carbon with a lone pair of electrons and metal with a positive charge. Now, you can also say it's an ionic bond. That's completely okay if you want to just look at a qualitative approach. Quantitatively, how much ionic or how much polarity there is, you can look at the electronegativity values. But you can always look at just the relative electronegativities between the two atoms to kind of talk about how much negative charge would carbon have and how much positive charge would metal have. But at the end of the day, what we're really looking at here is carbon having a negative charge and a metal having a positive charge. So I can write it like this, but I can also leave it like this, where eventually I want to think of in a sense that I got a negative charge on the carbon and I got a positive charge on this metal whenever I break this bond. So when I have a negative charge on the carbon, this carbon is going to be used as an nucleophile. But the problem is, along with being an nucleophile, this is actually also going to be on a strong base. So you have to be really careful whenever you're using these organometallics, because even though I'm creating a carbon that has a potential that can actually act as in a strong nucleophile, but it can also act as in a strong base. So I don't want to be using anything that's in a protic solvent. So whenever we're dealing with organometallics, we want to avoid the use of protic solvents. So what's a protic solvent? Something like water. I don't want to use that. I don't want to use methanol or any sort of alcohol, in a matter of fact, because what I can get instead of running this carbon as an nucleophile as in a base, and it can deprotonate those protic solvents. So I don't want to be using any of those protic solvents in those cases. A most common solvent that's used whenever we're running these organometallics, especially with the Grignards, we use ether. And whenever we use organolithium, we typically use like hexane or pentane or something like that. But I'll talk about those again. But those are not protic, so I don't have to worry about organometallics doing an acid-base reactions in those cases. So let's come down to some of these different ones. So I have an organolithium that's going to be the first one. Now remember, these are not the only organometallics that you would see, but these are the most common ones that you're going to be seeing in sophomore organic chemistry. So if I'm talking about organolithium, what I really got is in a carbon lithium bond. And obviously I can have a CH3, or generically I can just write this as an RLI. Now what I know about this bond is going to be very polar, or I can say very ionic, because lithium is way onto the left side on the periodic table. So there isn't a huge electronegativity difference. So I can rewrite this as an CH3 negative and an Li positive. And I can also, generically, if I want to write down as an R minus and an Li positive. So how do I really make it? So one of the common ways of making this organolithium is I want to use some sort of um, alkyl halide. So let's say I use RBr here, and then I use two equivalents of lithium. So what's really lithium doing in here is actually in a source of an electron. So it loses the electron. So another way of saying it undergoes an oxidation. So that means it's really acting as a reducing agent, because it's kind of reducing someone else. The R is going to be gaining those electrons at the end of the day. So what I get is an R minus, or I can say R Li, and then the second equivalent of lithium is going to be used to make this uh, salt in here. So the RLi, I can write this as an R minus and an Li positive as well. So I can technically use any one of those um, alkyl halides. Doesn't really have a lot of restrictions on those. Even I can use aromatics. and something like, let's say, chlorine here, two equivalents of lithium, and I should be able to make and a negative charge on that carbon with a lithium plus there. Or even I can rewrite that as something like this, and I'll have LiCl as my side product. So I'm creating an carbon with a negative charge in here, and the most common solvent that's used when you're dealing with lithiums is hexane. I can use hexane or pentane or anything like that. It doesn't really matter. Now, when you look at a Grignard, so Grignard is a little bit different. So it uses a magnesium as a metal instead of an lithium. So what I'm really looking in here is an RMGBr. So remember, magnesium actually can make two bonds as opposed to lithium only makes one bond. So that's why you only see like RLI here. But in case of magnesium, magnesium gets embedded in between the carbon and the bromine. So still magnesium gets in a 2 plus charge on here, obviously. But at the end of the day, what I'm really getting is, again, an R minus. And then I would have MgBr with a positive here. So what's really the difference in the R or the nucleophile or the carbon with a negative charge that you get from the Grignard versus the one you're getting from an organolithium? And if you want to kind of pay close attention, it's really the electronegativity difference. So think of, let me just going to write down generically, and a CH3Li versus CH3MgBr. So I can say that there is going to be a bigger difference in the electronegativities between the carbon and the lithium compared to an electronegativity difference between the carbon and the magnesium, because lithium is less electronegative than the magnesium. So as a result, this carbon would have even more a negative charge. You can think of that way. So as a result, organolithium tends to be more reactive than the Grignard reagent. However, they do a lot of similar reactions. So anything that Grignards can do is very likely the organolithium would also do. But if I want to just compare between those two, organolithium is going to be more reactive than the Grignard just because of the electronegativity differences. And it's not that they always going to be doing the same type of reactions. You would see eventually where there are a couple of reactions down the line where it would be slightly different for an organolithium and it would be slightly different for the Grignard reagent. But remember, for the most part, I would say 90% of the reactions that they do, like you're gonna learn in sophomore organic, if the first one is doing, the second one is also doing the same one. But there is slight differences that you would see eventually down the line in this chapter. So how do I make an Grignard reagent? I can use something like, let's say, CH3, CH2Br, and I use magnesium. And in this particular case, we use ether as our solvent, and I'll ended up getting CH3, CH2, MgBr. So who's providing the electrons in here is the magnesium. Remember, the magnesium can give two electrons as opposed to lithium was only giving one electron. So that's why we have to use 2 moles of lithium to get a full lone pair of electrons on that carbon, basically. But here, technically speaking, magnesium can give 2 pairs of electrons. And the ether actually helps to make that pair in case of, in this case, like you remember the ether is going to look something like this. So the lone pairs of that electrons on the ethers help to stack this R, this Grignard reagent. So it's kind of a unique help that it gets from the ether in that particular case. Now you don't have to have only this one. I can have technically any alkyl halide that is going to be able to make a Grignard. That includes the aromatic alkyl halides as well. And obviously, I didn't want to talk too much about the mechanism, but the whole point is just really who's losing the electron and who's gaining the electrons at the end of the day here. Okay, then I have an organocuprate. Now that one is a little bit different than what we have talked about the top two so far. Organocuprate is typically made from the organolithium. So I would have So the formation of organocuprate actually comes from the organolithium. So I can have, let's say, 2 moles of organolithium, and I can just say CH3Li here, and then I use copper iodide, so CuI there. So that has a 1 plus charge on that copper. And eventually, since I'm using 2 moles of those, it gets attached to two of the coppers in here twice, and then that gets a minus charge on this copper because you're getting two of the CH3s there, and then you're going to have the Li kind of embedded with it. But a lot of time when you look at an organocuprate, you may not see the charges or may not worry about the charges, but rather this might be written just something like CH3 to CuLi. And another way of writing it, I can just write it R2CuLi. But what I'm really getting at the end of the day from the organocuprate is again an R minus, or I can say a CH3 minus, or it can be any alkyl groups. It can be alternate aromatics as well. So what's really the difference in there? Now, if I go back to the electronegativities in here that we were discussing earlier, we have in a carbon lithium bond, we got a carbon magnesium bond, but now all of a sudden we get in a carbon copper bond. So that one I can say is not going to be as polar. You can say like, the electronegativity difference is even smaller when we compare the carbon and copper in this case, because copper is way kind of in the middle of the periodic table. And as a result, you do get a negative charge on that carbon, which can possibly act as a nucleophile, but it's not going to be as strong as you would see in case of carbon magnesium. And obviously, carbon magnesium is not as strong as you would see in case of carbon lithium. So that's the difference. It's really the electronegativity difference that plays an important role here. So as a result, this the R negative, typically you're gonna get the nucleophile that you're gonna get from the organocuprate is the least reactive out of those three. And because of that reason, it does a lot of different reactions. So whatever you see in case of organolithium and Grignards, there is a good chance that you're not going to see that with organocuprate. So that's the beauty of it. So sometimes you don't want to use a very strong nucleophile, so as a result, you want to go for an organocuprate in that particular case, and we'll see some of those reactions. But for right now, make sure you know the differences between some of these organometallics. Now, finally, I want to kind of finish this lecture here with the organoacetylide. Now, this is something that you may have already seen in case of an alkyne. So remember, when you deal with an alkyne, especially in a terminal alkyne, you have a bond, a carbon hydrogen bond that's relatively acidic. So I can use something like NaNH2 to kind of deprotonate that, or even NaH, you can use that to deprotonate that. And as a result, you get a carbon with a negative charge that can potentially act again as a nucleophile or as a base. So I don't want to be comparing the organoacetylides with any of those three up there because the nucleophile that you get from the acetylides is not going to be exactly the same because it possesses the triple bond in there, as opposed to the nucleophiles you were getting from, the organolithium, Grignards, and organocuprate. They were actually very same. So as a result, you were able to compare their relative reactivity, but I don't want to be putting the relative reactivity of the acetylides with them. That's just in a totally different one, but this can again act as an nucleophile and as an base in these reactions.